and record. Cool. So what we did yesterday is we talked about a conversion of an alcohol to an ester in the synthesis of aspirin. And then we talked briefly about turning alkanes into halogenoalkanes. And we talked briefly about turning alkenes into alcohols. And all I said was basically we're not going to take yesterday's lesson as done lesson. Yesterday was just an example of the kind of functional group conversions that we're going to be constantly looking at. So that yesterday's lesson was just an introduction to functional group conversions. And if you missed it, it's fine because you didn't really miss anything important. Okay, so I've got these notes. They are uploaded onto Google Classroom, so you can go download them later. I did say on Google Classroom, they are not final. And the reason they're not final is because I'm busy editing them at the moment. And as I'm editing them, I'm coming up with new ideas of things that I want to add to them. So for now, the notes are just there so that we can get through the lesson. But what I will do is at the end of probably this week sometime, I'll sit down and I'll edit the notes. And I want to try and get the format to look more or less the same. And I want to get the sort of feel of the notes to have a general flow, which I haven't quite worked out yet. So for now, they're just temporary notes just to get through the lessons. Cool. So if you remember last year from IGCSE, we talked about alkanes, and we said that they were generally unreactive. So I do link page references here to your textbook, so you can go and read about these in the textbook. In other words, you can go to the textbook and you can cross-reference these over here. So when we talk about combustion, we're literally saying put it with an excess of oxygen and turn it into carbon dioxide and water. Now, strictly speaking, this would not be a functional group conversion because carbon dioxide itself is not really a functional group. So strictly speaking, it's not a functional group conversion, but it's something that you can do with an alkane. You can combust it in oxygen to form carbon dioxide and water. And yes, there was bond breaking and there was bond forming. So technically speaking, you have formed different functional groups, but in reality, all you've done is created two gaseous products, carbon dioxide and water. Cool. And then you get incomplete combustion, which is exactly the same thing, except that you have insufficient oxygen. And instead of producing carbon dioxide, you produce carbon monoxide. And this is the less favorable of the two because carbon monoxide is poisonous and poisonous to our health and to the environment, whereas carbon dioxide is the lesser of two evils. Cool. So these are not really functional group conversions. They're just something you can do with the alkanes. So you won't find this on the functional group conversion chart. Cool. And then side note, this is just something interesting. You can go and revise this. Recall that we can measure the volume of CO2 and then we can calculate the amount in moles. And then we can use the amount in moles to calculate the molecular formula of the alkane that was combusted. So I haven't given an example of this, but I'll just give you an idea. If I tell you that some alkane was combusted, so we don't know what alkane it is, and it's complete combustion, meaning there's excess O2, we can measure the amount of carbon dioxide produced. So we can put it into a gas cylinder of sorts and we can measure it. So let's say, for example, 240 decimeters cubed was produced. That's a large volume. I'm just making up numbers so that we can get the idea. Cool. Then you're going to have to remember that 1 mole is equal to 24 decimeters cubed per mole. So it means that you can convert this volume. You can convert this volume here. Undo divide by 24, and that'll give you 10 moles. Which means that when you write your balanced equation, you're going to say that if 10 moles of CO2 was produced, it means that I had to have 10 moles of carbon. And the only alkane that has 10 moles of carbon is C10H, H 10 times 222. So we have done this in class. I'm not going to go through it in detail now. If you want to ask questions, you can Zoom me later. But we did do examples like this where we calculated the amount of carbon dioxide given off. And from the amount of carbon dioxide given off, we could calculate the molecular formula of the alkane that was combusted. Any questions? I mean, we're not going to go through it in great detail, but would you like to ask any questions?
So when we talk about functional groups,
Sure.
does this include a type of bond specifically?
Well, in this case, we were told that it was an alkane. So in this case, it was mentioned in the question that this was specifically an alkane. So it only had carbons and hydrogens.
Okay.
But I think your question was slightly unrelated because I don't think you meant it in this context. I think you meant it in a different context.
Yeah, no, because like when you were saying when you combusted, it's not strictly speaking a what do you call it, conversion. So I was just thinking because like I read somewhere that it's also a type of bonds. I'm just a bit unsure.
Yeah. So you can look at the bonds in carbon dioxide. So if you wanted to, you could say that this starts as all carbon-carbon single bonds, which we could say is the so-called alkane formula. And over here, you could say you end up with that, and you end up with that. And if you really strictly want to call these functional groups, you could think of this as being a carbonyl. You could think of it as being either a ketone or an aldehyde. So you can think of this as some sort of ketone. And then you could think of this as being some sort of alcohol group over here. But yes, we have changed the configuration of the bonds. So yes, functional groups are related to the type of bonding, absolutely 100%. Cool. So functional groups has everything to do with the type of bond present. Cool, but strictly speaking, these are not ketones and these are not alcohols. They are and they aren't. It depends really what you want to use them for. Okay, cool. So what is useful, this is something we've never done before. This is a brand new reaction. So this is quite interesting, is that we can react alkanes with halogens. And in this case, the halogen is either bromine or chlorine. And we can create the halogenoalkane, which we've seen before. One of the specific conditions is that it has to have a large amount of UV light, meaning that it would occur at room temperatures because there's UV light in the spectrum of our light. But in order to speed up the reaction, we would give it a large amount of UV light. So we would put it into a UV light filter of sorts. Cool. And it's not particularly useful, and you'll see on the example on the next page, is because we can often get a mixture of products. So what we can do is we can say, starting with methane, we can take the methane, we can add chlorine, and we can end up with chloromethane. Then we can take that chloromethane, we can react it with more chlorine, and we can get dichloromethane, and so on and so forth, until you end up with the product that is only carbon with 4 chlorines. In other words, the alkane no longer exists. Cool. But the problem with this is that you have to keep it very specific. In other words, if you want to create only the first one, you have to get your mole ratios absolutely correct. So I'll give you an example of how this will work. In order to create just the first one, so if you wanted to create that one, it means that you have to start with 1 mole CH4 and you have to add 1 mole of Cl2, and that'll give you 1 mole of the CH3Cl. The problem is the minute you start adding excess of this, so once this becomes in excess, you're going to start producing things like that. Does that make sense to everyone? Do I need to explain that again?
Yes,
Yeah,
so
thumbs
please
up. Good,
repeat.
good, good, good. So that makes sense. In other words, we have to be very, 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 very controlling of the reaction so that we don't end up with products that we don't want. Otherwise, what we're going to end up with is a mixture of what we're going to end up with is a mixture of that. And we might not necessarily want that, because maybe the only thing we want is this. So we only want this. So we want this and not this. Cool. So look carefully at each molecule. Can you determine what the name means? So like I said, we're just going to learn naming in context. So let's have a look at the names. The first one, which has one chlorine, what do you notice about the prefix? Does it have a prefix? Does it have anything in front of the chloro?
No.
No, it doesn't have anything in front. Cool. So that's when there's only one chloro. Cool. Then you look at this one. It has 1, 2 chlorines. You get dichloro. Cool. And then you look at this one. You have 1, 2, 3 chlorines, and you get trichloro. And then you have here 1, 2, 3, 4 chlorines, and you get the tetrachloro. So without learning the rules of naming, do you kind of see that there's a relationship between the number of chlorines and di, tri, and tetra? There's a relationship between di is equal to 2 chlorines, tetra is equal to 3, and sorry, tri is equal to 3, and tetra is equal to 4. Cool. So everyone happy with that? So we'll talk about namings as a whole topic on its own, but it's good to learn it in context. So you're basically going to learn the naming rules as we go along, as we talk about molecules. Okay, so we can start with propane. And what we have to do is we have to be very specific here, and we have to say that if we add 1 mole of this, and if we add 1 mole of this, what we're going to end up with is 1 mole. I'm going to get rid of this one, just erase it over there. We're going to end up with 1 mole of that. In other words, if I add exactly 1 mole of chlorine, I'm going to add exactly 1 mole of propene. I'm going to end up with 1 mole of that product over there. Cool. And then do you notice that the name here is 1-chloropropene? 1-chloropropane. Cool. So let's have a look at the name and see if we can figure it out. Let's have a look. The 1 is telling me that it's on the first carbon. There's no di, tri, or tetra, so it's just 1 chlorine. And then the propene is telling me that it's 3 carbons. So it's 3 carbons, and there's 1 chlorine added somewhere in that molecule. So 1 chlorine, and there's the chlorine over there. 1 chloropropene. Now, in an ideal world, in a perfect world, I would get only that product. In a perfect world, if that's the product I wanted, I would get only that product, meaning I wouldn't get anything else. None of this would exist over here, so none of that would exist. But it's not a perfect world, and unfortunately, I can't control this reaction. And what I end up with is a mixture of products. So what I end up with is I end up with a little bit of the one on the left, and I also end up with a little bit of the one on the right. And what you notice here is that the chlorine is now on the second carbon. So I've got the 2-chloropropane. Cool. So it's still only 1 chlorine, so it's still monochlorine. It's still just chloro. There's no di, tri, or tetra. But now the chlorine is on the second propene. And what you'll find is that in terms of a mole ratio, you'll end up with a 1 mole of total products. So 1 mole of total, but you'll end up with a ratio of 45% of the 1. So 45% and 55%. In other words, I'm going to end up with a mixture of both, and those two added together is going to give me 1 mole. So if I add, if I add those two together, that's going to be 1 mole is going to be equal to those two added together. Cool. Any questions?
No.
No, everybody good? So
Yes.
would you say that this, yeah, talk to me, please ask questions.
Could you explain the 1 mole divided and the both together again, please?
Okay, good, very good question. So what I'm basically saying is that if I start over here on the left-hand side, if this is just 1 mole, so if I start with 1 mole of propane and I add 1 mole of chlorine, what we're going to say is that I'm going to end up with 1 mole of products. When these are not added together, it's not 1 mole plus 1 mole. It's saying that that 1 mole of products is going to be shared between the two of them. So in other words, of that 1 mole, some of it will be this and some of it will be that. and then they give you the ratio at the bottom, and they tell you that 45% will be the left one and 45 will be the right. So maybe what I'll do is I'll write it for you, then you'll see what I mean. This will be 0.45 mole, and this will be 0.55 mole to give a total of 1 mole. That makes more sense.
Yeah.
Yeah,
Thank
that
you.
makes more sense. And then the statistical, don't worry about that. The statistical is not important. The statistical is basically saying, based on their simulations and based on their hypothesis, what they think would have happened, they would have assumed it would have been 75, 25, but that's not what we observe. What we observe is 45 and 55. So would you agree with me that it's not a particularly useful reaction because I'm going to end up with a mixture of products?
Yes, sir.
Yeah, but it is possible to separate them. So what I say here at the bottom is it is possible to separate a mixture of these two products, but that's an extra step in your process. In other words, if I only wanted the one on the left, I need to get rid of the one on the right. And if the one on the right is not particularly useful, I'm basically just going to throw it away, which means I've wasted half of my starting materials. So I've actually only created half of what I could have from a starting point. So that's what we can do. And basically the functional group conversion that we're talking about here is when you go to your functional group conversion intros, the functional group conversion we're talking about is this one over here, taking alkanes, adding ultraviolet light with a halogen at room temperature and pressure to create the halogenoalkane. So we've ticked that off the list. So that's one functional group conversion that we can take off our list. Cool. Any questions so far? Please feel free to ask questions at any time if you have any ideas or thoughts or something you'd like to add. Good. So you can go through those examples. Then, strictly speaking, cracking is not technically a functional group conversion. It is and it isn't. It's just it is a functional group conversion, but it's not. We're not taking an entire molecule and turning it into one other entire molecule. What we're doing is we're breaking the molecule apart. So you remember this from last year. Cracking is taking a large alkane and breaking it up into a smaller alkane and a smaller alkene. And in the strict sense of the word, it's not a functional group conversion, but loosely speaking, you could think about it as being taking an alkane and turning it into alkene, but it's not one molecule turns into one molecule, it's one molecule turns into many molecules. So if this top one here is the alkane, if this is the alkane, then this is the alkene. But you remember you also get the other alkane with it. So you don't just get alkane to alkene, you also get one alkane into a different alkane. Cool. And then what you'll notice with these things is that the total number of carbons and hydrogens always add up. And what you can do is you can separate it in as many different ways as possible. So here's another example, the exact same molecule, but broken up slightly differently. So if you count the number of carbons here, you have 1, 2, 3. And if you count the number of carbons here, you have 1, 2, 3. And then if you add a different color, you'll see that this is 4, 5, 6, 7, 8, 9, 10. And then 4, 5, 6, 7, 8, 9, 10. But what we've created in the second molecule, in the first molecule, is we've created the double bond. So there was no double bonds in the first carbon over here. So there's no double bonds. And over here, we have a double bond. So we've created a double bond. We've removed, well, we haven't removed 2 of the hydrogens. What we've done is broken a carbon-carbon bond. The hydrogens on that carbon went to the one side and the other side had to form a double bond because carbon always has to have 4 bonds. So if you imagine breaking, let's call it this bond over here, it's basically saying that one hydrogen went to the right. Yes, more or less. Yeah. Okay. Yeah, it's a bit difficult to see, but you can kind of use your imagination. There was a bit of hydrogen swapping around, but you would see that most of the hydrogens went to the right-hand side, and the left-hand side was left with fewer hydrogens. So instead of forming 4 carbon to hydrogen bonds, it now has to form a double bond so that it can have 4 bonds. You can think about that later when you go through it on your own. Cool. So if you look at the example at the bottom, if you count the number of carbons, it's 2 on this side, it's 2 on that side. If you count the number of carbons here, it's 12, and 12 is equal to 6 plus 2 plus 4. So 6 plus 2 is 8, 8 plus 4 is 12. And then if you look at the bottom one, 20 over here is equal to 8, plus 3 is 11, 11 plus 9 is 20. And in this case over here, we've created 2 alkenes. So these are, oopsie, get rid of that. What we have over here is 2 alkenes. And you can literally crack a large molecule into any different proportions. You can crack it into very big alkanes and very small alkenes, or you can sort of calculate it as half-half or any sort of proportionality between the two. Oh, but the total number of carbons before has to equal to the total number of carbons afterwards. Any questions on that? Good. Nobody has a question. Good, good, good. Okay, so that's basically alkanes. Alkanes are pretty useless. They're generally unreactive, except for the fact that we can combust them. So combustion is one thing we can do with them. Oopsie, I need highlighted. We can combust them. We can substitute them, and we can crack them. And there's obviously many more things you can do with alkanes, but not in your syllabus. For your syllabus's purpose, you don't need to know anything else other than that. Good. Any questions? You good?
Yep.
Good, good, good. Okay, let's take a 5. Oh, how much time do we have? We're allowed to go until 10:30. Let's take a 10-minute break and come back in 10 minutes.